The Western Sydney International Nancy Bird Walton Airport runway project represents one of Australia's most ambitious airfield surfacing undertakings, and Boral plays a central role in delivering its high-performance asphalt system. Spanning 3.7 kilometers, the runway incorporates reinforced concrete thresholds at both ends, with specialized asphalt placed through the central operating zone and all connecting taxiways. In total, more than 150,000 tons of asphalt will be produced, transported, tested, and laid with precision to meet the extreme demands of modern aircraft operations. Boral was selected from a short list of major surfacing contractors thanks to its integrated supply chain, proven performance record, and ability to control material quality from quarry to finished surface. Aggregate is sourced from Boral's Dunmore and Peppertree quarries, where targeted geological assessments identified the most durable and stable rock for airfield pavements. Blasting, excavation, mobile crushing, and multi-stage screening are coordinated to generate consistent single-size aggregates meeting strict airfield specifications. On-site laboratories continuously test gratings, binder content, stability, and compaction to guarantee durability under heavy aircraft loading. To support production, Boral deployed its T400 mobile asphalt plant, the largest mobile facility in the company's fleet. Transporting, positioning, and commissioning the plant demanded detailed engineering, multi-agency logistics, and critical lift procedures using 160-ton cranes. Dry drums, silos, hot bins, and conveyors were installed on concrete foundations constructed by DMG, Boral's civil division, over a tightly sequenced 14-week program. Working with CPB surveyors, the team delivered excavation, reinforcement, formwork, and precision concrete placement to support the plant, storage systems, and weighbridge infrastructure. Once operational, the on-site asphalt plant provides faster truck turnaround, reduced fuel consumption, and tighter quality control. Approximately a dozen trucks operate in continuous loops between the plant and runway, supplying 2 paving crews supported by MTVs, dual pavers, rollers, and quality control teams. Each shift targets production exceeding 2,000 tons, with hot joint management, edge cutting, and millimeter-accurate leveling to ensure a uniform, load-resistant surface. Surface priming, using a carefully blended kerosene and bitumen spray, creates an interlayer bond and protects the granular pavement from moisture prior to paving. Quality oversight is uncompromising. Field technicians use nuclear density gauges to verify compaction, while laboratory teams monitor every batch in real time. Any deviation from specification triggers an immediate production stop to ensure airfield safety is never compromised. Built to serve for the next century, the runway demands exceptional smoothness, structural strength, and water-shedding performance to meet global aviation standards. As construction progresses, the project stands as a defining engineering achievement for Western Sydney, an opportunity for teams, families, and future generations to take pride in shaping a major gateway for Australia's aviation future. Along the southern edge of Germany, near the shores of Lake Constance, a major pavement rehabilitation project is underway on the 96 highway. Over a stretch of more than 6.8 kilometers, contractors are renewing both the base and binder layers, requiring traffic to be diverted to the opposite carriageway to create a continuous working corridor. Into this environment rolls one of the most capable asphalt pavers ever built, The Vogel Super 3000-3i, a machine engineered for extreme output and absolute precision. The Super 3000-3i delivers extraordinary performance with a maximum paving capacity of 800 tons per hour, paving widths up to 18 meters and layer thicknesses up to 50 centimeters. For this project, the contractor cutter GmbH & Co. Kilogram relies on the machine's ability to place both structural layers seamlessly across a full 12-meter width, achieving exceptional smoothness and optimized pre-compaction in a single pass. At the heart of this performance is the new rigid Vogel SP350 screed, featuring a base width of 3.5 meters and heavily reinforced beam geometry designed to maintain cross-slope accuracy under massive load. Configured in its high compaction version, the screed uses a tamper and 2 pressure bars to deliver outstanding density before rolling even begins. Operators can adjust the tamper stroke hydraulically, switching between 4 and 8 millimeters at the push of a button, ensuring ideal compactive effort for each layer. For the 14-centimeter base course placed here, the 4-millimeter setting provides optimal results. To maintain uninterrupted material flow, 2 Vogel Mount 3000-2 offset power feeders work in parallel, continuously supplying the paver while being alternately reloaded by waiting trucks. This synchronized feeding system prevents delays and enables nearly dust-free placement of up to 4,000 tons of material per day. The Erga Plus 3 operator platform provides full visibility and intuitive control, while Vogel's multiplex ski system ensures millimeter-accurate leveling by averaging sensor readings across multiple points. The Super 3000-3i is powered by a robust 6-cylinder diesel engine delivering 354 kW, yet even under these demanding conditions, Eco Mode provides ample performance with low noise and fuel consumption. With its Stage versus Compliance and Eco Plus emissions reduction package, the machine sets new benchmarks in efficiency, cleanliness, and paving excellence. The demolition of the Gardiner Expressway's eastbound ramp stands as one of the most complex bridge removal operations ever executed in Toronto. 10 major bridge sections dismantled over a single weekend, amplified by supersized equipment, relentless coordination, and minute-by-minute precision. Work begins simultaneously on both the eastbound and westbound lanes along Lakeshore Boulevard. Crews split the deck, breaking concrete in 2 directions to expose as much structural steel as possible before the heavy lifting begins. This early phase relies on precision breakers, high-reach excavators, and tight sequencing to keep the job moving safely and efficiently. Across the site, every discipline is engaged. From office engineering teams to field laborers, project managers, superintendents, and crane operators. Safety drives every decision. Spotters monitor machine movements, riggers inspect lifting gear, and supervisors track the condition of each structural member before cutting. It is teamwork on a city-scale stage. Massive lattice boom cranes position themselves at pre-engineered pads to begin hoisting down steel girders. Before the first lift, operators must crawl beneath the bridge to perform the initial breakthrough cuts, a task taken on by the most experienced personnel. Once the cranes are rigged, each beam is lowered with multi-point slings to maintain balance and prevent torsion. Every lift occurs under strict communication between the signaler, crane operator, and ground crew. As the iconic structure comes down, logistics rule the job site. Thousands of tons of concrete and steel must be handled without delay. Material is segregated immediately. Concrete to one stockpile, rebar to another, structural steel to a dedicated zone. Trucks must navigate beneath hydro lines, merge into live traffic, and cycle continuously to keep the pad clear for incoming debris. With cranes staged at fixed positions, haul routes cannot change, forcing planners to choreograph every truck movement like clockwork. By night, the pace intensifies. Under tower lights, crews continue breaking decks, torch-cutting steel, and sweeping debris from the workface. The process follows a strict sequence: break, clear, cut, lift, load, repeat. And while the tempo is fast, workers maintain a rhythm born from experience. Excitement at the start of the weekend settles into focused momentum as everyone adapts to the flow of the operation. The demolition is executed in staged weekends. Lessons from the first weekend are carried directly into the second, tightening workflows and boosting efficiency. With experience gained, production accelerates. Deck demolition progresses eastward. Concrete vents are removed beyond the Don River, and girders west of the river come down cleanly and on schedule. Behind the scenes, advanced engineering underpins every cut. The team begins with 3D scanning, capturing exact bridge geometry and any undocumented modifications accumulated over decades. Digital models are built with high-level detailing, allowing engineers to calculate load paths, analyze cut sequences, and verify clearances for cranes and equipment below. These models ensure that demolishing one part of the structure does not unintentionally overload another. Engineering oversight continues until the final piece is removed. No shortcuts, no assumptions. On the bridge deck, up to 10 excavators operate simultaneously. Below, another fleet handles ground protection, debris removal, rigging, offloading, and transportation. The first weekend alone generates enormous volumes of concrete, temporarily staged on-site to maintain uninterrupted braking cycles. Efficient material management determines the speed of the entire operation. For the demolition team, the project represents a powerful combination of scale, challenge, and pride. Many workers are second or third generation, standing shoulder to shoulder with family members who have built their careers in heavy civil demolition. For them, the Gardiner job is not just another project, it is a landmark moment. Executing the largest single-structure bridge demolition in the company's history requires unmatched planning, flawless communication, and relentless safety discipline. As the final girders come down and the debris field clears, the operation stands as a testament to engineering rigor and the skill of the crews on the ground. It is demolition at its highest level, performed safely, efficiently, and precisely on time. In the heart of downtown Seattle, a massive construction operation unfolds, one that showcases planning, precision, and non-stop teamwork. Brundage Bone Concrete Pumping and Hoffman Construction come together for one of the most demanding phases of any high-rise build, the mat pour. This is the foundation of the entire structure, and it has to be done right. The scale is enormous. Over the course of 18 straight hours, concrete trucks cycle in and out of the site, delivering more than 700 truckloads of material. In total, over 7,000 yards of concrete are placed into the foundation, enough to shape the structural base for a major tower. To keep up with this pace, Brundage Bone operates 5 high-capacity concrete pump trucks positioned strategically around the site. Each pump works continuously, sending thousands of gallons of concrete through long boom arms and into the mat foundation. The coordination is intense. Trucks arrive one after another with precise timing to prevent any interruptions in flow. A mat pour of this size must stay continuous to maintain structural integrity, so every minute counts. As each truck empties its load, it pulls away and another takes its place, creating a carefully choreographed rotation that never slows down. Lighting towers push back the darkness as the work continues through the night. Noise from pumps, trucks, and finishing tools blends into the steady rhythm of progress. As the final loads arrive and the last sections are placed, the mat begins to take shape as a single, solid slab, engineered to support the immense weight of the building that will rise above it. On the ground, crews from Hoffman Construction guide the placement with skill and attention. Workers monitor depth, coverage, and consistency, while teams use vibrators and rakes to ensure the concrete settles evenly with no air pockets. Throughout the operation, supervisors track temperatures, mix quality, and pump performance, key factors in a pour that lasts nearly a full day. By the end of the 18-hour window, the job is complete. 7,000 yards of concrete, flawlessly delivered, and expertly placed. It's a true demonstration of teamwork, logistics, and the experience of Brundage Bone and Hoffman Construction, another major milestone set in concrete in downtown Seattle. The One Za'abeel Phase 2 Link Bridge Lift marks a defining engineering moment in Dubai's skyline. Suspended between the twin towers of One Za'abeel, the massive structure stretches 226 meters in length and rises nearly 100 meters above the ground. This final lift completes one of the most ambitious hoisting operations ever attempted in urban construction. Engineered as the world's longest cantilevered building, the link is a monumental 500-ton steel structure that demanded absolute precision in planning, synchronization, and load control. Specialized strand jacking systems gradually elevated the bridge into its final position, millimeter by millimeter, while teams continuously monitored structural behavior, cable tension, and tower deflection throughout the lift. Given its extraordinary weight and geometry, engineers developed a staged lifting sequence that balanced the load between both towers. ensuring structural integrity from ground level to the final elevation. Temporary supports, spreader frames, and real-time instrumentation were used to stabilize the bridge during every phase of the operation. With the successful completion of the final lift, the link bridge now stands as a landmark of modern construction technology, an elevated, cantilevered marvel that seamlessly connects two towers while redefining what is possible in high-rise engineering. The 700 TPH iron ore wash and beneficiation plant in Australia, developed for CIMIC mining, showcases a fully integrated CDE processing solution engineered for high-throughput performance. The system begins with the M4500 wash plant, cutting at 530 seconds to deliver precise initial sizing and efficient scrubbing. From here, material enters the lump ore beneficiation circuit, where advanced jig gravity separation works in tandem with high-capacity dewatering screens to produce a clean, stable lump product. 17 static and radial conveyors manage seamless material flow across the site. Fines are processed through a dedicated beneficiation circuit, featuring cyclone, slimes removal, and spiral gravity separation for optimized recovery. 2 of 1,500 units complete the operation with closed-loop water recycling and robust sludge management for sustainable continuous production. Jerplan tilt-up is a sophisticated method of constructing concrete structures widely used in commercial, industrial, and institutional buildings. The system is centered around casting concrete panels horizontally on site and then tilting them vertically into their final positions. This approach streamlines construction schedules, enhances structural efficiency, and reduces labor intensity compared to traditional poured-in-place vertical forms. The process begins with precise site preparation. The foundation slab, which will double as the casting bed, must be level, flat, and strong enough to support the weight of wet concrete panels during casting. Embedded anchor bolts and lifting inserts are positioned according to structural and architectural plans. Accurate placement of these embedded elements is critical for ensuring that panels can be lifted and fixed correctly. Concrete casting is the next stage. High-performance concrete, often with admixtures to enhance flow, durability, and curing characteristics, is poured into the horizontal forms. The casting process is carefully controlled to avoid segregation, ensure full encapsulation of reinforcement, and minimize air voids. Vibrators and other consolidation techniques are employed to achieve uniform density throughout the panel. Concrete strength is continuously monitored, with specific curing periods required before lifting. Once the concrete has reached sufficient structural strength, panels are carefully lifted using cranes or specialized lifting equipment. This is the hallmark of the tilt-up process. Jerplan uses engineered lifting points embedded in the panels during casting. The panels are tilted into vertical positions using hydraulic or crane-assisted tilt systems. The lifting operation requires meticulous planning, accounting for wind loads, panel weight, and rigging angles to maintain safety and prevent damage. After the panels are raised, they are temporarily braced and secured until permanent structural connections are made. This includes anchoring panels to foundations, connecting them to adjacent panels, and integrating steel or concrete structural elements as necessary. Openings for doors, windows, and mechanical systems are carefully aligned during this stage to ensure accuracy. Gerplan tilt-up also incorporates precast elements and architectural features. Panels can include embedded insulation, decorative facades, or integrated utility conduits. This reduces the need for secondary construction activities and accelerates the overall schedule. Additionally, tilt-up panels provide excellent fire resistance, sound insulation, and thermal mass, contributing to the long-term sustainability and energy efficiency of buildings. Quality control is integrated throughout the tilt-up process. Each panel is inspected for dimensional accuracy, concrete strength, and surface finish. Non-destructive testing methods, including ultrasonic testing and core sampling, are often used to verify internal quality. On-site monitoring ensures that lifting and bracing operations adhere strictly to engineering tolerances. Safety and logistics management are critical. Tilt-up panels are heavy and pose significant risks during lifting and placement. Gerplan emphasizes detailed planning of crane operations, lifting sequences, and rigging configurations. All personnel involved are trained in safe tilt-up procedures, including emergency protocols and communication standards. After each tilt-up wall panel is lifted into its final vertical position, a system of temporary braces is immediately installed to stabilize the structure. These braces, typically high-strength steel pipe shores, are anchored into the slab using chemical or mechanical anchors and bolted securely to the embedded inserts cast into each panel. Their purpose is to prevent any out-of-plane movement caused by wind loads, vibration, or construction activities. Field engineers verify plumb alignment using laser levels and adjust brace tension to ensure the panel stands perfectly vertical according to design tolerances. The braces remain in place until the permanent structural connections, such as roof diaphragm ties, panel-to-panel joints, and structural steel interfaces, are fully completed and inspected. Gerplan tilt-up construction represents a highly efficient, technically sophisticated approach to modern concrete building. Its combination of on-site casting, engineered lifting, precise panel fabrication, and integrated structural design allows for rapid, safe, and environmentally conscious construction. This method is increasingly favored for large-scale industrial, commercial, and institutional projects where speed, durability, and long-term performance are critical. Once the walls are structurally stable, the surface preparation and painting phase begins. The concrete is cleaned using pressure washing, light sandblasting, or mechanical grinding to achieve the required adhesion profile. All imperfections, including bug holes, form lines, and recesses from lifting inserts, are filled with polymer-modified repair mortar or epoxy compounds. After the surface reaches the specified moisture and cleanliness levels, a high-performance anti-alkali primer is applied to seal the concrete substrate. These layers not only enhance appearance but also improve durability by reducing moisture ingress, limiting hairline cracking, and protecting the panels from weathering over time. Take a journey deep beneath the East Kimberley, into the hidden world of the Argyle Diamond Mine, the only operation of its kind and the source of more than 90% of the planet's rare pink diamonds. From the moment the camera passes Monty's door, the descent into the modern block cave system begins, revealing the immense engineering required to recover diamonds from hundreds of meters below ground. At the extraction level footwall, heavy loaders move through reinforced tunnels toward each draw point, where broken ore from the cave above funnels down to be collected. Further along the drift, an HD 40/40ths hauler transports the ore to the tipple point, where it drops into the bell crusher, beginning its transformation from rock to recoverable mineral. Electrical cabling lines the tunnel walls like a circulatory system, powering conveyor belts and lighting the narrow walkways beside them. Water draining from the rock mass is captured and routed toward the sump and pump station, keeping the workings dry and stable. Then moves through the underground workshop, the control office, and finally the refuge chamber, a sealed safe room designed to protect crews in an emergency. The mine unfolds as an intricate underground city built for one purpose: bringing Argyle's legendary diamonds to the surface.